to this Tango workshop on analytical methods in thermoacoustics. We are a very sort of small and intimate group here, consisting of the Tango Fellows and two of our speakers who have already arrived. I'd like to introduce those speakers quickly. This is Camilo Silva from TU Munich. He's going to speak today after my lecture. And next to him is Rafael Assier from the University of Manchester. And he is going to talk tomorrow. There is going to be a third speaker, Sebastian Dicroux. He was supposed to be here for today, but his flight was cancelled due to some strike. So he had to rearrange his journey. He's coming later, probably this evening. So he should be there for the lecture tomorrow. And yeah, unfortunately, the first lecture had to be cancelled. Susanne's lecture had to be cancelled. This is because Susanne was traveling with Gunilla yesterday to Manchester, from Stockholm to Manchester, and Gunilla was taken ill on the flight. So Susanne accompanied Gunilla back to Stockholm. They've arrived safely back, and it seems that Gunilla is not seriously ill. So there's probably no need to worry about her. Too much, that is. Right, I think that's enough of an introduction into the workshop. So without further ado, I'll just start with the first lecture, which is my own lecture on Introduction to Thermoacoustics Theory. Right, can you all see the screen? Right. I'll start. Here's a quick outline of my talk. First, we'll start with an introduction. In the introduction, we are going to look at the very basics. That's the conservation equations and some basic thermodynamic relationships. Then, in the second part, we are going to derive Lightill's analogy equation from first principles, and going to interpret the various terms in it so we can get a physical feel for it. And then in the third part, we are going to look at Rayleigh's criterion, which is basic, which can be derived from the same kind of equations as the analogy equation, and which is basically a simplified balance equation for the acoustic energy. But I'll talk about that in detail when we come to section 3. So let's start with the introduction and some basic assumptions and conservation equations. So we consider a fluid flowing with some velocity vector v, and that has in 3 dimensions 3 components, v1, v2, v3. Our fluid has density rho, pressure p, and we also have a viscous stress tensor sigma, which is a tensor with components sigma ij, and these sigma ij's depend on the coefficient of shear velocity, which is this eta here, and on these derivatives of these gradients of the velocity components. Right, so I'm sure you have all seen these conservation equations, but I would like to kind of emphasize the physics behind them, because I think just to see an equation is a bit boring. If you can see the physics behind it, it becomes much more interesting. So this is the conservation equation for mass, written down in 2 different forms, here just in vector form, here in component form. And what this equation says is that if you have a fixed control volume with a flow flowing in and out, compressing and whatever, it can do whatever it like, this flow. But what does not happen is mass is not created. So any change of the mass in the control volume is caused only because fluid flows in and out. That's basically the physics behind this equation. And then we also have a conservation equation for momentum. I've ignored body forces, so I'm taking a slightly simplified case, and that's again described by a differential equation similar to the mass equation, here in vector form and here spelled out in terms of components. And again, this is a conservation equation, and this says that if you have a fixed control volume, then the momentum in that control volume changes because mass flows in and out, bringing momentum with it, and also because forces are acting on the control volume. And here we just have these stress tensor, the forces due to the stress tensor. Okay, so these are the two conservation equations, and they're very basic equations. You can do a lot with them and you can derive a lot from them. Right, next some thermodynamic relationships. Let's consider a fluid element, so not a control volume, but a fluid element with a constant mass and undergoing a reversible process, like heat being added and the volume being changed. So if that fluid element undergoes these processes, its internal energy, which we call U, will change by an amount du, and this du is made up of two parts. The heat energy that's added, it's just the H here, and then the work done on the fluid element, which you can express in terms of this term, pressure times volume change, PdV. Right, when you add heat to a fluid, you change its entropy, and the change of entropy is given by this equation. ds is the change of entropy, is given by dH, this heat added over temperature. So far I've used kind of global quantities. It's common to, it's more convenient often to use local or specific quantities. So that's energy per mass or heat work per mass. So quantities per mass or specific quantities. Like the internal energy is the internal energy U. The specific internal energy, little e, is U divided by the mass. The heat energy is little h. The specific heat energy divided by mass, and the same for the entropy. Right, so the specific entropy changes if we add heat, and the change is given by this. ds is 1 over temperature times dH, the amount of heat added. Right, sorry, I'm going the wrong way. To work out the so we now know the dH in terms of a specific change. To work out the specific equivalent of the PdV, we need to do a little manipulation, which involves the definition of the mass density. Mass density is defined as mass per unit volume, so you can write 1 over ρ as V over m. And if you take this this term divided by m, you get a dV over m, so you can express that in terms of 1 over ρ, which has happened here. Right, and there's another quantity that's often used in thermodynamics, that's the specific enthalpy, typically denoted by capital B, and that's specific internal energy plus P over ρ. And the specific the change of the specific enthalpy of the fluid element is written down here, and it can be sort of rephrased with the various equations that we've already seen. Right, next I want to introduce the specific heat capacities. A heat capacity is the ratio of heat added to the corresponding increase in temperature. So the specific heat for constant density is denoted by CV, that's dH heat added per temperature, or by keeping ρ constant, and with ρ constant this derivative is equal to dE by dt and also to T ds by dt. So that's the specific heat for the volume, and the specific heat Cp for the pressure is dH by dt, keeping P constant, and that's equal, since we keep the P constant, equal to these expressions here. So these are the specific heat capacities. Right, when you add, without heat, the density is of a fluid, without heat addition, the density of a fluid is just a function of the pressure. That changes when you add heat. In that case, it then becomes a function of the entropy as well. So it becomes a function of two variables, pressure and entropy. So you can write the change of the density, the d rho, as a sum of two components. This one is due to the change in pressure, and this one is due to the change in entropy. And you're just using partial derivatives here, so d rho by dp, a constant entropy. That derivative we denote as 1 over c squared. So that's basically a definition of this c. which looks very much like a speed of sound, and later on we will see that it actually is a speed of sound. And this derivative can be, for an ideal gas, can be written like this, rho over Cp. And I've shown here the calculation that gives this result here. The starting point is the ideal gas equation, so d rho by ds you can write as d rho by dt times dt by ds with a chain rule. At constant pressure, the d rho by dt from the ideal gas equation gives this term, the dt by ds from the definition of Cp gives this term, so you combine it and you get that which we have here. So if we sum all this up, we can say that if you have a certain mass, element of mass, its density changes according to this equation. d rho by dt is given by, in terms of the change of pressure, dp by dt, and in terms of the change of the entropy. And that is an important equation. I've put it in a pink box to highlight it. I'm going to come back to that. Right, so that's the basics. Let's now move on to Leitel's acoustic analogy, and I'm going to try and derive it in detail. Right, so what we are going to do is we are going to consider an unbounded fluid filling all of space, but only in a finite region within that space we have sources. That's heat sources and vorticity sources. So in a sort of localized region we have these sources, and everywhere else we have an unbounded uniform medium at rest with density rho naught and pressure P naught. So I've indicated that here at the edge we have a uniform mean density and mean pressure, and here is our source region with heat sources. These are the orange dots, and turbulence. These are the pink little curvy arrows. And these sources radiate a sound field, which is indicated with the blue lines. And the aim is now to derive a governing equation for the pressure, just for the pressure, trying to get rid of the other thermodynamic quantities. And our starting point will be the conservation equations for mass and momentum. Right, so here we have our mass equation that we've seen before. There are quite a few sort of mathematical operations now. They're not particularly difficult. You just have to know how to do it. And if you know how to do it, it's no big deal. So the manipulation you have to do to the mass conservation is you have to add this term 1 over c naught squared dp by dt, where the c naught squared is this derivative, dp by d rho, at constant entropy. And the c naught, at this stage, is just a definition, but it will turn out to be the speed of sound. And the subscript s indicates that we have an isotropic process, in other words, no heat added. So if you just add this term to the mass conservation, you can write it like that. So that's basically just some terms added on the left and the right. It's exactly the same equation, basically. The momentum equation we are also going to manipulate, and what we're going to do is we are going to add on both sides this term, which is 0, because you can sort of get rid of the vi, and then also take vi outside the bracket, and then what you have left is the mass equation, and of course that gives you a 0. So you're just adding 0 to the momentum equation, and you can then write it in this form, which is called Reynolds form of the momentum equation. But again, it's completely equivalent to the original form of the momentum equation that we had. Right, so our mass equation has become this, our momentum equation has become this. In the next step, we are going to differentiate the mass equation with respect to time. The momentum equation, we take the gradient, so d by dxi on both sides. So we differentiate, as I've indicated here, and then the resulting equations we subtract from one another, and that gets rid of these terms with the rho, vi, vj in it. And what you get is this equation in the pink box, which is a very nice equation. It's basically a governing equation for the pressure P. On the left, sorry, I'm going a bit too fast. Yeah. We have these constants in there, the P naught and the rho naught. These were just constants that we sort of inserted at random without making any mistakes, and it's a kind of convention to do it like this. And then we have on the right-hand side this term, which has got a special name. It's called the excess density, and I'm going to abbreviate that with rho E. So what we have here is the wave equation term, the Bernstein wave equation term on the left for the pressure, and then some extra terms on the right to complete the equation. Right, here's the same equation again. And I'd like to emphasize that this is an exact equation. We have made no simplifying assumptions, no linearization, no assumption that the mean flow is zero, nothing. So this is a very, very general equation. Let's just sort of see what happens if we consider a simpler case, a case where there is no source region. No vorticity, no heat added, no heat sources, where the motion is linear and where the viscosity effects can be neglected, so that sigma I is zero. In that case, the whole right-hand side is zero, and what we get is this, the well-known equation, wave equation for the pressure in a medium, in a sort of unbounded medium without any sources. Right, so that shows us that we have basically a wave equation for the pressure with source terms in this equation. And it also shows us that C naught is a propagation speed of the acoustic wave. Right, so yeah, here I've derived the analogy equation in this form with the pressure in the on the left-hand side. An alternative is to do the manipulation in a slightly different way and derive an equation with rho, the density, on the left-hand side. That's directly equivalent. I've described here how it's done, and what you get when you do all this is a similar equation which has on the right-hand side just this sort of double derivative with respect to position x. And this is the sort of original form of Lytle's acoustic analogy equation. That's the classic form of it with this double derivative on the right-hand side. And the term that's being differentiated on the right-hand side, this term here, is called Lytle's stress tensor. For our purposes, this form isn't very handy because we are especially interested in the heat added, and that's kind of tangled up a bit here. A more convenient form for us is this equation, because that term will turn out to be directly related to the heat added, and it's just nicer to interpret that form physically. Right, let's move on to the interpretation. Excuse me, I'll just switch off the air conditioning because I get a constant cold draft. And it's really uncomfortable.
Excuse me, Maria.
Yeah?
When you said that this is an exact equation with no approximations, wasn't isentropic process an approximation for that?
Oh, that was just in one little manipulation, but not in the overall assumptions to derive the equation.
Okay.
Yeah. Okay. Here's our analogy equation. I've simplified that term a bit, or not simplified it. This term here, I've expressed in terms of the excess density that we've introduced a bit earlier. So that gives us this term, and then here we have the stress tensor term and the vorticity term. Right, and it's a good idea to sort of rewrite the right-hand side so we can interpret the individual terms, and this is what I'm going to try and do next. For that, we are going to use this relationship which we've derived in section 1.2, where we expressed the change of density of a mass element in terms of change of pressure and change of entropy. And I'm not going to show the mathematical manipulations. Anyway, with that equation, we can rewrite this source term as follows. Sorry, no, just this source term as one with the excess density like this. And then the complete analogy equation becomes all this. On the left, as before, just a simple wave term, and on the right we have various source terms that we are going to identify. This one is the entropic term that includes the change of entropy, that term. I'll skip to the last one. This is Leiter's quadrupole term, and all the rest in the middle is typically referred to as indirect combustion noise. And we are going to look at that in a bit more detail. So here's that source term again that we just seen on the previous slide. And this term is the entropic term. It's related to the heat release rate. By using this relationship, relating the change in entropy to the heat added, we can see that this is directly related to the heat release. So that is, from a thermoacoustics point of view, a very important term, because it's the primary source term when you add heat. Then we have, the next term is this one, and these two lumped together, which we have here. These terms are significant. You can see there are changes in pressure and density. So these terms are significant when there are regions of unsteady flow with different mean density and different sound speed. So there are certain circumstances where these terms become important. And then this term, this last term, this term here describes the effect of momentum changes of density in homogeneous. So if you have a hot spot with a lower densities of being accelerated through a blockage, say, it's this term, you get a sound radiated from it, and it's this term which describes the sound radiated by this accelerated hotspot. Right, so that was a quick run through Leiter's acoustic analogy. And I now want to turn to Rayleigh's criterion. And in preparation to that, we are first going to derive a balance equation for the acoustic energy. So not the whole energy, but the acoustic energy. And our starting point, well, first our assumptions are a bit different now from before. We have a pressure which is composed of a mean part P naught and a fluctuating part P dash. The P naught is constant. Same for the density. For the velocity, we just have an oscillating velocity, no mean flow, and also no vorticity. And we assume that the viscous stress tensor is 0. So these are our underlying assumptions. And the next thing to do is to manipulate the mass and momentum equation, conservation equations, a bit similar to what we did before. I mean, manipulate in a different way so we get the result that we want. Okay, so I'll describe briefly the manipulations. They're basically, again, just mathematical steps that are very straightforward if you know what to do. So the mass equation, you multiply by this expression, acoustic pressure over mean density, and then you get this term. You multiply this on both sides. You get these nonlinear terms or quadratic terms like P dash times dP dash by dt. Now, you can use a little trick here and say, this is the outcome of the chain rule if a differentiator squares. So if you work backwards, if you differentiate dP dash square by dt, if you differentiate that out with the chain rule, you get the inner derivative, dP dash by dt, and the outer derivative, or vice versa, P dash. And it's a similar story with that term. And also we have linearized here, so only P dashed is still in there, but the rho dashed, that's sort of part of this rho, has been neglected, and the rho naught in there has been cancelled with that rho naught. And here we have our source term as before, and we can express that in terms of the heat added, in terms of the Q dashed. Right, so this is what we've done to the mass equation. And the momentum equation, we do a similar thing with it. Here's our momentum equation for our simplified case. We multiply both sides with the velocity component ui and get this equation. And then again, we use the chain rule in reverse, as it were, to rewrite these sort of nonlinear terms, the u times du by dt as a du squared by dt, and similarly with that ui dui by dx, and we linearize, so the uj term disappears. Right, so we have these two more complicated form of our of our conservation equations, and we add the two, and if we rearrange the terms nicely, we get this equation, which has a very direct physical interpretation. So in the first term we have a time derivative of two terms here. I'll start with this term because that's easier to interpret. This is a half times density times velocity squared, so that's a kinetic energy density, kinetic energy per unit volume. That one on before it is the potential energy density. So in there we have the d by dt of potential plus kinetic energy density.
So a question, I mean, there is not a dash in U as well?
Because I assume that there's no mean flow, the u dashed and the u are equivalent.
Ah, okay.
And then we have this term, this gradient of pressure times velocity. That's the acoustic energy flow. I'll demonstrate that in a moment. And on the right hand side we have a rate of energy gained per unit volume. This is not so obvious from a local form, which this is. This is a local form of the acoustic energy balance. So to make it more intuitive, I'm going to convert that into a global form where we can actually see what's happening in terms of a fluid flowing through a controlled volume and heat being added.
Excuse me, Maria.
Yeah.
Did we have an assumption of constant density somewhere?
No. No,
there's a slide in the middle when we took out rho.
Yeah. So we have, this is our density. The mean density is constant, but on top of that there's a fluctuating density which obviously can fluctuate.
So in the next slide, and in this second line in the middle, what was the assumption there? I couldn't follow.
This one?
No, the top one. Yeah, right there.
Yeah, the UI with the Alex is very small, and you are multiplying it with P prime, which is also very small.
Yeah, you have to be a bit careful here, because we are linearizing, but we are linearizing an equation which is non-linear. But if you sort of forget the fact that we have sort of made it non-linear simply by multiplying with a P dashed, then we are back to linear. And that can be that equation can be linearized, okay, by assuming that products like p dashed times rho dashed or p dashed times u or rho dashed times u are negligible.
Okay.
So we assume that the fluctuating quantities are very small, so that products of them can be neglected compared with the first order terms, with the terms themselves.
Okay, but what I saw here was that, well, it looks like that rho is not dependent on xi.
Here.
You're right, it's rho naught plus rho dash.
Yeah, so
and you'll get the rho naught that cancels out with the 1 over rho naught, and then p dash rho dash that cancels out because
Okay, yeah.
you linearize.
have you seen it?
Yeah, I got
Okay.
it, yeah.
Okay. Right, so we've derived this local version of the acoustic energy balance, but to convince ourselves that this really is an acoustic energy balance, let's convert that into a global version, which is easier to interpret. So we have, we assume that we have a control volume V, which is indicated by this violet ellipse, with a surface S of V, and in that control volume we have a source region with heat sources. Right, so actually I haven't shown the conversion, I've just written down the sort of global form. So basically what's happened from the previous slide to get this equation is we've integrated over that volume, and we've made use of the fact that we have a gradient in there, and the integral over that can be expressed in terms of a surface. The volume integral over that can be expressed in terms of a surface integral. Right, so here we have, you can see the integration over the volume here has taken place. So we have the d by dt as before, the time derivative. This term is the potential energy. This is the kinetic energy, so we are integrating the energy per unit mass over the volume, so that gives us the whole energies. And the two together with the time derivative amount to the rate of change of the acoustic energy, E. And then on the right-hand side, we have the loss of the acoustic energy, that sort of is energy that is lost at the surface, that flows out, due to pressure variations and acoustic velocity. And this term represents the gain of acoustic energy from the heat source. It has the heat release term in there, the Q. So if there was no rate of heat release, this term would be gone. And we just have a balance equation saying that the acoustic energy changes because energy flows in and out through the surface. And here we have an extra term now, which represents an energy gain from these source regions. Sorry, from this source region. Right. And this energy balance is actually rather useful because we can say it's of useful indicator for stability. Because if we have an unstable system, the energy, the acoustic energy of that system will grow with time. Okay, in the long run. Over a long time, it will grow, and not from one sort of point in a period to another. But in the long run, if the acoustic energy grows, we have an instability. So this is.
How do you define the Q here? I missed it maybe on the last slide.
I think it's the heat release per unit mass. I can't remember 100%. I think it's per unit mass. It may be per unit volume, but I think it's mass. It's one of those. But I normally use mass, and I think I've done it here.
And what are the assumptions for this one about fluctuations in mean values for Q?
For Q, none. So
it's general form, like
it's a general for Q. Q has not been linearized. Q is a mean heat release plus a fluctuating heat release, and nothing has been. The Q hasn't been touched. Right. So this energy balance tells us that we have an instability if the energy keeps on growing in the long term or averaged over a long time. And if losses are absent, so if this is absent, we can say that an instability occurs if this integral taken over, where the product P times Q is taken as in a time average. If this is greater than 0, we have an instability. Right, just a quick remark before we move on to Rayleigh's criterion about extensions to the balance equation. We've ruled out mean flow, but people have actually done the case with mean flow. In fact, there are several versions of the balance equation it's no longer called the acoustic energy, it's called the disturbance energy then. Anyway, there are several versions of it. Just for your information, that these extensions do exist. And also it's been extended for rotational flow, which is an assumption that we've excluded. I'm not going to show how to do these extensions, just for your information, they exist. Right, back to Rayleigh's criterion now. So we could infer from the acoustic energy balance that we have an instability if this integral over the source volume is greater than 0, and our integrand is the time average of pressure times rate of heat release. And this time average, if that's positive, we have an instability. And when is it positive? It's positive when those two quantities, P dash and Q, are in phase or roughly in phase. And that's basically Rayleigh's criterion. So basically Rayleigh's criterion is a simplified version of the acoustic energy balance. It neglects losses, such as radiation losses. If you have a one-dimensional case, you have radiation, a tube with open ends, you have radiation losses at the ends. they are neglected by Rayleigh's criterion. If you have losses in boundary layers or vorticity, all that is neglected, but it's kind of the most basic form of the acoustic energy balance. Acoustic energy changes due to heat added. And if the heat added and the pressure, acoustic pressure, are in phase, we have an instability. Yeah, so it's not an empirical finding. It's actually it's a consequence of the basic equations of fluid mechanics. And that brings me to the end of my lecture. Thank you very much.
So how do you choose Q? How do you the source, the term, the heat release? How is it defined?
It's defined through the global heat release. So the global heat release is heat energy, a rate of heat added. It's a rate of heat, not a heat. It's a rate of heat.
Yeah, these are coming. So I guess it depends on the configuration. If it's the richer tube, there is an expression for Q.
Oh, yeah. So I haven't said anything about how Q is linked to the acoustic field.
Because generally, I think that's where the empirical part of the model comes in. That's
right. Yes. So that's the really tricky part, knowing how the heat release rate is related to the acoustic field and any other properties of the field. And there are a lot of different ways of expressing that, and there are measurements trying to measure the relationship. There are theories, there are some numerical simulations. This is a massive field that I haven't touched on at all. I just assume that we have a rate of heat release which somehow depends on the acoustic field.
When does the mean flow become important? Is it when the Mach number becomes larger at a certain value, or is it?
When does mean flow become important? If you have just a very simple one-dimensional configuration, then you can neglect the mean flow for acoustic purposes if your Mach number is small. That means if your mean flow velocity is small compared with the wave propagation speed, and that's often the case in a combustion, certainly in a Reike tube, in a flame tube, where the mean flow tends to be of the order of meters per second, and the speed of sound is over 300 meters per second. But there are cases where it becomes important. For example, if you have a low Mach number flow and then you have a blockage, and for the flow to go through a blockage, it has to speed up. And if it sort of reaches high Mach numbers in the blockage, it becomes important. So there are cases where the mean flow becomes important. Yeah?
I didn't study thermoacoustics before. I just have a very, very rough idea. And after your presentation, I'm just trying to make things settle down on my mind. That's why I'm asking. Perhaps it's a very, very obvious thing. From the Rayleigh criterion, if we reach that, if we satisfy that criterion, it says it might have instability. It's not set, but if it is smaller than zero,
yes,
or equal to zero, it is stable. We can definitely say that, right?
Yes.
Okay. Yeah.
But it can be positive and stable
yes,
if you take into account the losses.
That's
So
it.
the threshold is difficult to establish.
Taking account the losses over here, it can compensate the.
Yes.
Yes. Yeah, exactly. You can have a positive energy gain, but still stability because your losses are bigger than the energy provided by the heat source.
Thank you.
Yeah.
So the only criterion for neglecting the mean flow is just the Mach number as far as it's.
I've neglected it to keep things simple. I always want to sort of explain things without extra unnecessary complications. And there was going to be a lecture by Susanne this morning about mean flow acoustics. So unfortunately, that we couldn't hear. But generally, sort of as a rule of thumb, I would say if your mean flow velocity is significantly smaller than your speed of sound, you can neglect it. Neglect it for acoustic purposes, not when you look at the rate of heat release. So if your rate of heat release depends on velocity, then the mean flow becomes important.
For the acoustic, then if you consider the mean flow, you can just, instead of having just the Helmholtz equation on the left-hand side of your left, you probably have what's called convected acoustic equation. You just the same sort of linear one, but with a big U considered constant and some stuff there. And but that goes through.
Right. Any other questions?
In the extension of the acoustic energy, when you were talking about vortical, also,
Yeah.
it was carried out by who? This extension?
How?
How? Okay. Okay, it's how it is.
Yeah. Yes.
Okay.
Any other questions?
And it's the source terms. Is really continuous, like the big source term in thermoacoustic systems, and all the other terms like viscosity are only loss terms, or are there some other significant source terms which are now neglected in this analysis?
You mean positive source terms?
Yeah, exactly.
That's of enhance and instability.
Exactly. Yeah.
The only other positive source term I can imagine is if you had an active control system. And so you have a secondary source, and you feed that with a phase shifted signal of your sound field. And if you choose your phase shift in a certain way, you can sort of convert that source that secondary source into a source that sort of adds acoustic energy. So it is a bit like what you're doing in your project. You're trying to construct a rig with a virtual flame. It's exactly that. So your flame is your virtual flame is a loudspeaker fed by a sort of processed form of the acoustic field. But other than that, I can't think of another of a physical process which could lead to an energy gain. Yes?
Usually when we solve the aeroacoustic problems, the light field and energy, we will use it for the far field without some boundings. The equations you derived just now, is it possible to use it in the duct just now?
The equation, I've shown them for the three-dimensional case. If you want to use them in a duct, just reduce them to one dimension. It's very straightforward.
So do we need to change the green function or something?
I'll come on to that in my next lecture. In my next lecture, I will talk in detail about the one-dimensional and three-dimensional green function. Right. Any other questions? No? In that case, let's finish with my lecture. What's next on the program? Lunch. We have at 12 o'clock.